Good morning.
Good morning. Morning. All right, good morning. If I can have you all turn on your videos, please. Just get in the habit of doing that. That would be great. So I have to mention that every time. I don't have very many announcements today, but I will say I'm getting a lot of messages from students. I could have anywhere from 20 to 40 messages when I'm done for the day, and I'm spending all my night, trying to questions. So one thing you can do to help me out is either send them in the remind or the email. Don't do both. So I have students sending me a remind message, they send me an email, and you're doubling. So now instead of having 40 messages, I have 80. So please just, if you could just send a message in the remind, that would be really good. So just send a message in the remind if you're trying to tell me something. Just don't do it in both. So do one or the other, but if you could send the messages and remind, that would be really good. All right. We are working through the prerequisite section. And like I said, for those of you who have never had some of the things I'm talking about, you might have to put forth extra effort. I don't know what else to tell you. I haven't even started the pre-cal class, and we're still in the prerequisite section. I'm okay with that, but I'm just letting you know that we need to perhaps put forth, more effort on just trying to get up to speed so we can actually start the class. You're going to have on Friday morning. Now, P2 was the properties of exponents, and I'm going to try my hardest today to give you time to work in the new groups. So the new groups aren't completely new. Your new groups have at least 1 or 2 new people. So I'm trying to strategically change these groups around so that everybody has the opportunity to meet somebody by the end of this class. So if you have any questions today for me on the properties of exponents, make sure you ask me. But you are to take that exam on 8 o'clock on Friday morning. Make sure you take it. You cannot miss an exam. If there's some type of emergency, you could take it earlier, but you can't take it later. So I expect everybody to take that. Make sure you set a bunch of alarms so you're ready to take it at 8 a.m. That's P2. Today, what I'm planning is I'm planning on teaching half the time and the other half to allow you to ask questions in groups and ask me questions. So what I want to do is I want to finish P3. I'll be honest with you, in P3, they're teaching a month of Algebra 2 in one section. So they're assuming that you've had this before. And so I'm going to try to give you as many hints, as many problems as possible. This is intense. There's a lot of stuff. So anyhow, so to get started with P3, anybody want to ask me any questions right now about anything? I got an email about the hotspot. So if you're somebody who needs a hotspot, they ran out. So you're going to have to wait until they notify me, notify you about a hotspot. But what I would do is I would email or call the principal or one of the assistant principals and say, hey, I need this internet. When are you going to get it? When can I have it? So guys, look at these 45. the problem with this section is there's 8 objectives. So I don't know if you guys noticed all the pages that you would have to read through if you had to read through them. And you don't want to have to read this. You want to just look up something if you don't understand it. But there are 8 objectives. When I'm in my math meetings, you know, the Algebra 1 teachers are teaching 1 objective a day. I'm like, I'm not teaching 1 objective a day. I'm teaching like a million objectives a day. So I don't know if they really get that or not, but this is 8 objectives. So if you look at the lesson, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 sections. So not only is there 8 objectives, but there's 11 that I have to test you on. So let's just look at on page 45, let's look at what I've done, okay? All right, so in problems 1 through 12, I showed you about a perfect square, and I showed you about square roots and how you have to have 2 for 1 to come out. Number 13, I showed you how to do a prime factorization, how to break down a number or how to break down the variables to get things out of the radical. Now, I was hoping that we would only cover square root, but we're not. We're covering cube roots, fourth roots. We're looking at all kinds of radicals in this section. Problem number 23, I showed you how to get radicals out from underneath how to get fractions out of the radical by splitting them up, and how to rationalize the denominator. So if you have, that doesn't mean you know it. Also, I don't know if you noticed, but in the assignment for P3, I put a list of properties in your assignment so you'd have those at your fingertips. So there's a bunch of properties. So I put a list of those in your assignment so you can look at them. Okay, number 33, that's what I want to start with. Okay, this is adding and subtracting radicals. So let's start with adding and subtracting radicals. Now, I'm going to do that. And if you look at number 45, that's rationalizing more denominators. Look at number 55. Those aren't square roots. That's a cube root. There's fourth roots. So I have to explain those. Like what you do when you have. We do. Same thing with 67. And then on 75, you're adding and subtracting nth roots. And then to top it off, we go into fractional exponents. And fractional exponents are called rational exponents. Rational, fractional mean the same thing. All right, so let's take a look at this. All right, just a crash course on this. When you're adding and subtracting radicals, you have to have the same index. Must have the same index and same radicand. So remember that this is the index, and when you have a square root, it's invisible. And this is the radicand, remember that? So if you were adding these, you can't add them. Why? Because you have the same index, but you don't have the same radicand. So you're just stuck. So if this was 3 times the square root of 2 plus 4 times the square root of 2, you can add those. And it's like terms. All you do is add the 3 and the 4, and you leave the radical alone. So it's like combining like terms. You know, with like terms, you have to have the same variable raised to the same power. Same thing here. You have to have the same index and the same radicand. So these are pretty straightforward once you understand the rules. So if this was 3 square root of 7 minus 2 square root of 7 minus 5 square root of 7, the negatives together, so this would be 3 radical 7, and a negative is a negative, and you add the front, but you leave the radical the same. So it's like terms.
Mr. Birch.
Mm-hmm. Go ahead.
I can't see the bottom, like, cause like your camera is like not all, like I
I'm
see like,
sorry.
yeah,
I'm
yeah.
sorry.
No,
My bad. My bad. Can you see it now? Speak to me, please. Can you see it now?
Yeah, I can.
Okay, sorry about that. Okay, so that's that. Now, what happens if you have something like this? Now, that looks like you can't do anything with it. It's like she just said we have to have the same radicand. Those have the same radicand, but guess what? There's people hiding out in there. So when you do a prime factorization on 8, so remember I built that upside down cake? You can do this when you're ahead. 8 is 2 times 2 times 2. There's a 2 hiding out. So when you take the 2 out and you multiply that, you get 10 radical 2 minus 3 radical 2, and there. Now we can subtract them. So this would be 7 radical 2. So that's the thing. If anybody's hiding out, you got to get them out of there to see if you have like radicals. So we thought that there was nothing to do, but there were some guys.
Ms. Birch, for example 3, how did you get 3 2s? Is it because of the where it says 3 to the power of 2? I mean 3 2 squared? I don't know what I'm trying to say.
It's okay. Like, it's okay. I got you. I got you. Watch. Remember the other day when I did a prime factorization, we broke down the 8 and I pulled out the primes. Remember that?
Yeah.
That's what I'm doing. I'm doing a prime factorization off to the side of my paper. The reason why you didn't see me do it was because the smaller numbers we should be able to do in our head. You're like 6 is 2 times 3. 8 is 2 times 2 times 2. 12 is 2 times 2 times 3. So we want to be able to do these small prime factorizations in our head.
Okay, that makes sense.
Yeah, yeah. Do you see what you see where I got it though, right?
Yeah, I do.
Okay.
Thank you.
Now, don't try not to do things on the right. Try to do this stuff on the left in the margin. So don't do it in line with your work either. So these prime factorizations should be done in the margin on the left. Let's do another one. I might be doing some out of your book. So when you look at this, it's like, we can't add those. But look at there's ones hanging out here. So the prime factorization of 18, what I would do, in my mind, I'm just going, okay, well, 18 is 3 times 6 or 2 times 9. It doesn't matter which one you use. So I'm just going to say 2 times 9. Well, isn't 2 times 9 2 times 3 times 3? And 50, isn't 50 5 times 10? So wouldn't 50 be 5 times 2 times 5? 5 times 10? Are you guys following me or not? Please unmute yourself and just let me know you see what I'm doing.
Yeah, I see what you're doing.
Yeah.
Others of you?
Yeah, I do.
Okay, does anybody that's watching this meeting, does anybody not understand what I'm doing? And I'll show you over here.
Can you just go over it one more time? Just because.
Sure, no problem. So over here, 18, if I take out a prime number, it'd be 2 times 9 or 3 times 6, whatever. It's going to work out. It's going to work out correctly, whatever numbers you pick. So 9 would be 3 times 3. So the prime factorization, see the 2 times 3 times 3? And then 50 would be either 5 times 10 or 2 times, 25? And then 25 is 5 times 5. So see, however you do it, the order is going to be mixed up. Remember, multiplication is commutative. So 2 times 5 times 5 is the same as that. Okay, did you follow me that time?
Yeah, I get that. That was way easy. Yeah, thank you.
Okay, here we go. So a 3 gets to come out. So when he comes out, don't add your multiplying. So 3 times 3 would be 9, radical 2, and then a 5 gets to come out. See, there's 2 of them. So 5 times 5 is 25, and a 2 gets stuck. So now look at like radicals. So this would be 9, and that is what, 34 radical 2? And so this is a 3-step problem. You don't want to try to do this problem like in 1 step or anything. This is a 3-step problem.
Wait, how'd you get 9 again?
Okay, see this? There were two threes, right? So a 3 gets to come out. Well, when the 3 comes out, it's 3 times 3 is 9. Over here, when the 5 comes out, it's 5 times 5 or 25.
Miss Birch, so all you really did was just add 9 plus 25, and that's how you got 34?
That's right.
All right,
That's right.
Sure. Thank you.
Yep. No, you guys are, honestly, you guys are doing great. All those questions are really good questions. And just keep the questions coming because everybody is benefiting. Excuse me. Everyone is benefiting from the questions and the answers. So just keep them coming. You guys are going to do really well if you keep this up. The questions are important because, see, I don't know every little thing that you're wondering about. And so if you can ask and I can answer, we can get everybody's problems straightened out. Because it's not like you guys that are asking are the only people having problems. Everybody's having problems. There aren't 2 people having problems. There's 36 people having problems. So, okay, are you guys good with that then? You guys think you can practice this?
Yeah.
Okay,
Practice
Yeah,
with it.
That's good.
you guys good? You get what's going on though, right? Okay, now what I just covered is 33 through 44. Now I'm going on to problem 45. And 45 is rationalizing the denominator. Okay, so what's happening is, last time I taught the lesson, I told you that you could not have a radical in the denominator. So check this out. Can't have that. So do you remember what I said? You can't have any perfect squares under there. You can't have a radical in the denominator, and you can't have a fraction under a radical like this. You can't have this. And the index has to be as small as possible, which I'll show you later. So you have to get rid of him. So the question is, how do we get rid of them? Well, check this out. If I created 2 of them, I could put them under 1 radical. And if I could put them under 1 radical, a 5 gets to come out. So that's what I'm going to do. I'm going to create 2 of them. And I have to put 1 on top because that right there is multiplied by 1. We're not changing the problem. If this was a radical 7, I would multiply by radical 7 over radical 7. If that was radical 11, I'd be multiplying by radical 11 over radical 11. So whatever this number is what you're going to multiply by to get rid of it. So what happens here is we get rid of the radical because a 5 gets to come out. And on the top, when you multiply now, when we're adding, you have to have like radicals, but when you multiply, you just have to have the same index, which is square root. We're good. square root of 10. And those are not going to simplify because that's not a 10. That's a radical 10. So that is the answer. And so the question is, well, why is it simplified? Because there's no perfect squares under the radical, because there's no fractions under the radical, and there's no radicals in the denominator.
Wait,
So
so
that's how,
Rich,
go ahead.
how you got the 5 is because one has to come out, right? Like from the bottom?
Yes,
Okay.
that's how I got this.
Okay.
I'm gonna do another one.
All right.
But that, what you just said is right. All right, watch. Can't have that. Can't have a radical in the denominator. So we want to rationalize the denominator. So to get rid of them, we're going to create another one. And so what is radical 10 times 10? 10, right? And on the top, we get 2 radical 10. And it's like, oh, hold on just a second. Isn't this just a regular fraction? Like, shouldn't we simplify that? So can't we have to simplify all fractions, right? So can't we divide by 2 and divide by 2? So 2 times what is 2? 1 radical 10. And 2 times what is 10? 5. And that is simplified because it meets the conditions. Oh my gosh, look, it's the same answer. Weird, huh? There's no perfect squares under the radical. So don't think that's not 5 times 5. Remember, it has to be a perfect square. This is 2 times 5. So nobody comes out. We don't have any fractions under the radical, and we don't have any radicals in the denominator. So it is simplified. So whether it looks like it or not, it meets the conditions. Okay, are you guys okay with this concept?
Yes.
Hello, questions?
It's good.
Yeah, that's fine. You're good.
Okay. Okay, now I'm going to show you a little more advanced problem with the same thing, but you do need to know how to do it, especially for pre-cal. Okay, ready? Hold on a second, 3. Now this is a little bit different because there's a binomial or 2 terms under here. So we can't just multiply by radical 7 over radical 7. It's not going to get rid of it. This goes together. And you can't cancel the 3 because, I mean, some students think you can do that. Some students think you can do that. You cannot do that. Okay? You cannot cancel parts of a sum or difference. So let me show you what you can do. Let's say this was 6x plus 3 over 3. If you could cancel all 3, you could do it. So this would be 2x plus 1 over 1. You can do that, but you have to be able to cancel all 3. Cannot cancel parts of a sum or difference. Okay, now back to what I'm saying. Now, to get rid of this, to rationalize the denominator, you have to multiply by the conjugate. C-O-N-J-U-G-A-T-E. Now, the conjugate is exactly what you see. It just differs by sign. So if this was a minus, you would make that a plus. Now, the reason why we're doing that is because, do you guys remember the FOIL method? First, outer, inner, last. I'll show you real quick. X plus 2 times x plus 3. You multiply the first, the outer, the inner, and the last. You guys remember that?
Yes.
Yes.
Okay. When you do this conjugate thing, you don't have to do the full FOIL. So when you multiply by conjugates, the outer and the inner go away automatically. So all you have to do is multiply the first and the last. Now, wouldn't that be this times this? Would that be a -7? Okay, you go ahead and look at that. I got to turn on the air conditioner. Okay, did you follow that? 3 times 3 is 9. Radical 7 times negative radical 7 is -7. Talk to me,
Miss
please.
Birch. So the reason why it won't be a radical no more. I'm talking about like in terms of the 7 is because they can't, like, the radicals cancel each other out, right? So that's why there is no more.
Well, they got, watch, this is, okay, what you have here is radical 7 times negative radical 7, right? And wouldn't that be negative radical 7 times 7? So doesn't the 7 come out?
Oh yeah. Okay, yeah, that makes sense. Yeah.
Right?
Yeah.
Okay. So on the top, you have to distribute. So this would be 3 times 3 is 9 minus 3 radical 7. And all he does is float down. 9 minus 3 times radical 7. And I cannot cancel. See, if that guy was a 3, I could cancel all 3 terms, but we're stuck. Now, in your book, they're going to leave it. They're going to leave it like that. You can't leave it like that. You have to multiply it out. I'm not assuming you know the distributive property. So you have to multiply it out. On your exams, if they leave it like that, that's fine. But as far as your assignments go, I want you to multiply it out. Let's do another one, okay? All right. We want to get rid of the radical in the bottom, but it is require the conjugate. So in this case, the conjugate is radical 2 minus 1, radical 2 minus 1. Let's do the bottom first. So when you do the FOIL with 2 binomials, this is the product of 2 binomials, you multiply the first. So radical 2 times radical 2 is 2. 1 times -1 is -1. So this is 1. So remember with the FOIL method, with the conjugates, the outer and the inner cancel each other out. So on the top, the book's going to leave it like that, but you have to multiply it out. 5 radical 2 minus 5, you're going to distribute. 5 radical 2 minus 5, and you can just erase this because over 1 just means that's redundant. All right, go ahead. Anybody have any questions before we go on to cube roots and fourth roots? Anybody want to ask me any questions?
Hey, Miss Birch. So
Yeah.
what happens to the 1, the 2 minus 1? What happens to that?
Well, 2 minus 1 is 1, right?
Yeah. But like, what happened? Like, do we just not do
any
anything?
number, anything over 1 is itself.
Oh yeah, that's true. So it's just, what's the point of even putting it in? Yeah.
So since this is just over 1, we can just erase it. It's still over 1.
Yeah.
But we know that it's over 1. We just don't have to write it.
Okay.
Now, if the 1 was on the top, you have to leave it. But a 1 on the bottom, you can just get rid of it. Or just not show it, I mean. You don't get rid of it. You don't have to show it. So if you ever have just a 1 on the bottom, you don't have to show it on the bottom. Okay, any other questions before I erase this? All right. So now, supposedly, you know everything about square roots. Go ahead.
Te lo voy a mandar en línea aquí.
Alex, I need you to turn off your microphone.
¿Cómo se lo vas a mandar en línea?
Yo voy a dar aquí.
Alex.
Oh,
Ándale, pues, porque voy a ir al banco.
hello?
Alex, I need your microphone on. Anybody have any questions?
Sorry, my bad.
No, that's okay. Okay, you guys, I have to give you this table because now we're going into not square roots, but cube roots and nth roots. So when it's not a square root, it's called an nth root. And I got to give you this table. You're going to have an odd index. And this, I put this in your assignment section. You have an even index with a positive radicand. You have an even index with a negative radicand. And you have a radicand of 0. Now remember, the index is the little number outside the radical, and the radicand is what's under the radical. Okay.
Wait, Ms. Birch, what does that say? Does that say n? Wait. Oh, wait. N ninth root or?
Right here.
Yeah, at the top.
Even. This is odd index. Even
No,
index
the one that was like at the tippy top. It said like something like
nth roots. Nth roots.
Oh.
What that means is you can have a cube root. You can have a fourth root. You can't see that, huh?
No.
It means you could have a cube root, a fourth root, a fifth root. So that's what we're going into now. Those are called nth roots. So what I'm giving you is I'm giving you the case. I'm giving you the number of roots you're going to get. And I'm going to give you an example. Okay, so if you have an odd index, like 3, 5, or 7, can you guys see this, right? This stuff?
Yeah.
Okay, if you have an odd index, you're guaranteed 1 real root. So if you have the cube root of 8, you have 1 answer, 2, because remember you have to have 3 now for 1 to come out. So cube root of 8 would be 2 times 2 times 2, so a 2 comes out. Right? If you have the cube root of 27, that's 3 times 3 times 3, so a 3 comes out. So that's with an odd index. If you have an even index with a positive radicand, you get 2 real roots. And the roots are the answers. So for example, if you have the square root of 4, you have plus or minus 2. The square root of like 25 is plus or minus 2, 5. Now, you didn't see me do this earlier, and there's a reason why, and I'll explain it in a minute, but let me finish this. If you have an even index with a negative radicand, there's 0 real roots. Can't be done. There's imaginaries, but we're not talking about that right now. So for example, if you have the square root of a -4, can't be done. So let's see how you're supposed to write the answers. You're just going to write no real roots. The square root of like -25, no real roots. Can't be done. So there's actually 2 imaginaries, but we're not talking about. Okay, so then if you have a radicand of 0, there's 1 root and it is 0. So for example, if you have the square root of 0, the answer is 0. If you have the cube root of 0, the answer is 0. If you have the 4th root of 0, the answer is 0. So what am I talking about? Let's do some examples. If they give you a problem, now this is kind of confusing, but this is math etiquette. If they give you a problem, you don't have to put plus or minus because they're assuming the principal root, which is positive. It's only when you put a radical that you put plus or minus. So in this one, you would just say, the square root of 4 is just 2. However, if you were solving an equation and I asked you to solve this and you put the radical, so you say, okay, I'm taking the square root of both sides, you have to put plus or minus. So you might have to listen to this again, but I'm just telling you, if they give you a problem with an even index, they're wanting the principal root, which is positive. If you put a radical in a problem you're doing, you have to put plus or minus.
Miss Birch, was that for odd and index?
That's for an even index. So that one matched the even index, this right here.
The last one you just did, right?
This right here is a square root. The other problem I did, I was solving an equation. We're not solving any equations right now. I'm just telling you that later when we solve equations, when you put a radical, you have to put plus or minus.
Okay.
We're not doing that right now. All right, now, if you have like the 4th root of like 16, -16, can't have that. You can't have an index and a negative radicand. There's no real roots. So you can't have an even index and a negative underneath. Now let's say that it was the 4th root of just regular 16. Well, the prime factorization is 2 times 2 times 2 times 2. Because isn't 16 4 times 4? So that would mean 1, 2 gets to come out. Because now that the index is 4, you have to have 4 for 1 to come out. Now, this is where this gets crazy. Let's say you have the cube root of a -8. Well, I just got through saying when you have an even index, you don't have any real roots, but you can, look at, you can have an odd index and get a real root. So what happens with this negative, the negative gets to come out. Because watch, wouldn't this be the cube root of 2 times -2 times -2, because doesn't that represent -8? So a negative gets to come out. So this can be confusing. You have to have this table. And the thing is, since you're taking online tests, you have this available to you, but you got to be able to understand the table. When you have an even index, you cannot have a negative under there. When you have an odd index, you can have a negative under there. There's nothing's being said about the radicand. The radicand can be negative. So there is a real root, one real root. So I should have made an example like that. So if this was a negative cube root of -8, the answer is -2. Okay, do you guys have any questions about how to read this table or how to do the problems? See, you're guaranteed one root. And this would be the cube root of -5 times -5 times -5. So the answer would be -5. Now they can still get stuck under there.
And that would be an odd index, right?
That's an odd index. So that's an odd index, one real root, right? So what I'm trying to see is with an odd index, whether it's positive or negative, you're guaranteed one real root, whether it's positive or negative. So in other words, when you have an odd index, like radical 3, cube root of something, 7th root of something, 9th root of something, regardless of the radicand, it can be positive or negative, and you can still have a real root. So if this was a cube root of +8, the answer would be a +2. So in other words, you can have negatives under the radical when you have an odd index. You guys, can I erase this? I put this table in your assignment section. I made a printout if you want to copy the printout. Now, these problems over here, I'll just do this. I'll do some more. These are pretty easy problems. There's another section of more difficult problems of these. So let me do a couple of those. So that section was just making sure you understand the table. The next section is a little more complicated, like what? I should probably just let you look at it. So we need 3. So I'm going to do a prime factorization. So I'm going to take out a 2. So 2 times what is that? 16. I'm going to take out another 2. 2 times 8 is 16. Take out another 2. 2 times what is 8? 4. 2 times 2. So this is, don't forget to carry the index down. 2, 2, 2, 2, 2. So there's 1, 2, 3, 4, 5. And so a 2 gets to come out times the cube root of 4. So see how 1, 2 got to come out? And then a 4 got stuck?
That would also be odd index, right?
That's an odd index. Yep, so we're guaranteed one root. There it is. Look at this one. There's a property that I gave you in your note in the assignment that you could put this under one radical. And so if I put this under one radical, wouldn't this be 3 times 3 times 2 times 3? So since they have the same index, I can put these under one radical, right? So who gets to come out? Well, there's 3 3s, so 1 gets to come out, and a 2 gets stuck. Don't forget the index. So nobody got to come out because there was 3 and nothing, but since the index was the same, I can put it under one radical like I showed in the properties in your assignment.
Birch,
Yeah.
where do you get the 2 from again?
This?
Yeah.
Well, 9 is 3 times 3. 6 is 2 times 3. Right?
Okay, that
9
makes sense. Yeah, for sure.
is 3 times 3, and 6 is 2 times 3.
Yeah. And then the reason why you put 3, and then like, would that be considered like a third power, or no?
That's a cube root.
Oh,
So
cube root. Sorry.
Instead of a square root, like normally the square root has a 2 in there that's invisible, right?
Yeah.
But this is saying a cube root, which is requiring 3 of something for 1 to come out.
Okay. For sure.
Now, so basically what they're doing is they're giving you problems like you had before with square roots with these nth roots. So let me just show you one of these. We may not get into groups because I'm not even done with the lesson yet. And I got to finish the lesson. So let's say you had 4 times the cube root of 2 plus 3 times the cube root of, I want to do a harder one. It's too easy. 5 cube root of 16 plus 3 cube root of 54. So this is just like what we did before with square roots, but you need 3 for 1 to come out. So off to the side, you would do a prime factorization. 16 is 2 times 2 times 2 times 2. And 54, I have no idea, so I have to do it. So 54, I'm going to take out a 2. So that would be 27. 3 times 9, 3 times 3. So that would be 2 times 3 times 3 times 3. So who gets to come out? Well, 1, 2 gets to come out. So 2 times 5 is 10. And a 2 gets stuck. And over here, a 3 gets to come out. And a 2 gets stuck. And look at, you can add those are like radicals. Same index, same radicand. So the answer is 13 times the cube root of 2. Any questions? This weekend, if you need me to go through some of these, because this is a lot of stuff, and this is stuff you should have already had, but I don't believe you had it, and so it's not your fault. I'll be happy to, if you guys want to go over some problems this weekend, just let me know. Go ahead.
Just, I have one more question pertaining to that particular question right there.
Go ahead.
So you cross out the 3 3s and the 2 3s as well, like, or?
Well, they're 2 separate problems.
Yeah.
Over here, the 16, there were 3 2s, so 1 gets to come out, and over here there were 3 3s, so 1. They're like 2. See this plus sign? They're like 2 separate problems.
Okay.
Okay, you guys. Now I'm going to switch gears completely and go into rational exponents. Rational exponents are radicals. It's just a different representation. So basically, when a problem starts with a radical, work with radicals. When a problem starts with rational exponents, and this rational means fractional, work with fractional exponents. Now, this is going to be challenging to you because you've never done anything like this, so check this out. Okay, first of all, I should explain this. I should explain this. Okay, what I'm showing you right now is the equivalence of the rational exponent and the radical. So when you see a rational exponent, it really means the nth root of a to the 1. So for example, this is what I'm talking about. If you have x to the 2/3, it really means the cube root of x squared. So in other words, the denominator goes in the index and the top is the power underneath the radical. So let me show you another one. Let's say you have x to the 2/11. This is really the 11th root of x squared. So this is represented as a radical. This is represented as a rational exponent. Now, when you have a radical, it's easier to work with radicals. When you have a rational exponent, it's easier to work with those. Now, let me give you an example. When you have decimals, it's easier to work with decimals. When you have fractions, it's easier to work with fractions. It's the same concept. So whenever you have a rational exponent, try to work with those. Whenever you have a radical, try to work with those. So let me show you something. You don't want to change that to a radical. Okay, well, here's what you want to do. You want to say, oh, well, that's a perfect square. So isn't 36/6 squared to the 1/2? So look what happens. You multiply the exponent and the answer's 6. So this is all going to be very weird at first, but you'll get used to it and you'll love it. Like 100 to the 1/2 power. 100's a perfect square, isn't it? Watch this one. 27 to the 1/3 power. Let's say 2/3. Well, 27 isn't a square, it's a cube. So now we worry about cubes. It's like you're looking for special numbers. 27 is 3 times 3 times 3. So when you raise it to the 2/3 power, look what you get. 3 squared, which is 9. Same thing with 8 to the, let's say 8 to the 4/3. Well, 8 is a perfect cube. It's not a square, it's a cube. So we can write 8 as 2 times 2 times 2. And when we raise it to the 4/3 power, 2 to the 4th is 16. Okay, go ahead, I'll take questions. Any questions about this?
No.
To me, this one seems more easier than the other one we were doing before.
It is. It is. It's just that initially students don't like it because they're just not used to it. And so it's like, we don't like that because we're not used to it. But this is, you will like it. You will like it. So you'll have problems like this. Don't change them to radicals. Now, remember what the rule is? The rule says multiply the numbers, and when you multiply monomials with the same base, you keep the base and add the exponents. Well, don't you need a common denominator? So the common denominator would be 12. So don't you have to multiply this guy by 4 over 4 and this guy by 3 over 3? It's a lot of work. So this would be 14x to the 4 twelfths plus 3 twelfths is 7 twelfths. A lot of work. All right, I'm almost done. I'll do another one of those.
Do you add those or do you multiply them?
Well, remember the rule, the product rule that said when you multiply monomials at the same base, you add the exponents. So even though we're multiplying them, the rule says to add the exponents. Remember? Remember we had this? Remember that?
Yeah.
That's what you're being tested on Friday. Is the product rule. When you multiply monomials, you add the exponents. So that's the test on Friday, tomorrow. So this is x to the 2/3 cubed. Remember this property with the regular exponents? Remember you multiply the powers? Well, if you multiply the powers, can't you cross cancel? So wouldn't this just be x squared? So what am I trying to tell you? The test that you have tomorrow, these properties are the same. And you're going to notice the properties in your assignment. The properties are exactly the same that hold for the properties you're taking an exam on tomorrow. All right, now. In the conditions of simplifying radicals, I gave 4 conditions. So the conditions were, got to get all the perfect squares out, the perfect cubes, whatever, get them out. Can't have any fractions under the radical. You can't have any radicals in the bottom. And the last one I said the index has to be as small as possible. I want to address that. You do not have to worry about this condition except when you have indices that are big like that. Now, I just got through telling you, don't change this to rational exponents. Don't change rational exponents to radicals. But on this case, it's like, oh, hold on a second. See that 6 and 4? We have to change it to a rational exponent. Remember the 6 goes on the bottom, the 4 goes on the top, because we can simplify this. So wouldn't this be x to the 2/3? And then when we change it back to a radical, look what we did. We got the index to be smaller. And that's what it means to get the index as small as possible.
So you're just shrinking and shrinking and shrinking the index then?
Shrinking the index, exactly.
As much
Just
as possible.
shrinking the index.
Oh, obviously, yeah. My bad.
What's that?
No, I was like, my bad. I was saying the same thing that was right there because I was like, oh, you're just shrinking it, you know? Like the index. Yeah.
Look at this one. It's like something's fishy here because look at how big that index is. So we're going to write it using rational exponents. We're going to simplify this by dividing by 3, dividing by 3. So this would be x to the 3 times what is 6, 3 times what is 9. And then we change it back to the cube root of x squared. So we made the index go from a 9 to a 3. Over here, we made the index go from a 6 to a 3. So that's what it means to get the index smaller. And you don't have to worry about it unless there's a big index. You don't have to worry about it. Okay, that is P3. Okay, so you have P3, but what I want you to worry about right now, I want you to go into the new groups and introduce yourself if there's somebody new. And then what I want you to do the rest of the time until 10:45, I want you just to ask questions and study work problems for the test tomorrow in P2. Okay, you can ask me questions about P2 or P3, but I want you to, you're going to look at your book under P2, and you're just going to pick out problems. So when I made the exam, I just went through and picked out problems in the section. So you're going to go through and take turns, pick a problem and work it as a group, check your answers, and call me over if you need me. All right?
How many problems are in the exam?
There's between 20 and 25.
Okay.
So don't forget that you have to show your work on scratch paper and you have to submit your scratch paper, and I'm not taking anything late. So the test is 60 minutes, and then you have 15 minutes to submit your scratch paper, and I'm not taking any late work, and I'm being real strict about it. So anybody turning anything late, I'm like, I'm not taking any late work. It's causing me too much work. So you got to turn everything in on time. Does anybody want to ask me any questions before I dismiss you to go into the teams? Okay. Well, you can hit me up on the, go ahead.
How can I get into the teams, because it looks like I'm still in the same one.
Maybe you are. Like I said, I only switched a few. So
Okay.
you may be with the same team, but you might have one new person. Who's talking to me, Jessica?
Yeah.
Jessica, you have one or two new people. So the
Okay.
teams will be changing, but they're not changing dramatically.
Okay.
All right. So if there's a new person in your group, introduce each other. Like I said, the teams will change, but I'm trying to do it a real systematic way so that everybody gets to work with each other. So the teams didn't change that much, only by one or two people. Okay, I'm gonna let you go. Call me over if you need me. Class is over at 10:45. Okay, I'm gonna be taking attendance in these teams, so make sure you show up. All right, call me over if you need me. We won't be reporting back either, so I'll be taking attendance in the teams. All right, class is over at 10:45. All right, I'll see you there.
Ms. Birch is not letting me go into